Hi, welcome back to the mathematics course. I'm Adam Jacobson, your lecturer. Today we'll discuss functions with more than one variable. And before we have discussed functions with only one variable. So why are we then interested in functions with more than one variable? Well, it's because in economics we quite often use functions with, well, guess what? More than one variable. For example, a production function. A firm producing something uses capital and labor. So there are two variables, capital and labor. And for what combinations of capital and labor do you get certain amounts of output? How much can you produce if we input 1 unit of labor and 2 units of capital, for example? Also in utility theory, consumer theory, so let's say I'm a consumer, I eat apples, that's one variable, how many apples, the other variable is how many oranges I eat. And then my utility function is a function of that, so the more apples and oranges I eat, the more happy I get, usually. So today then we'll look at some examples of these functions with more than one variable. We're going to focus on the two variable case, although all the reasoning can be generalized into functions with more than two variables, but we'll stick to two, that's enough. And we'll also illustrate that graphically so we can get a picture basically of how functions like that look. Then we'll also move on to the partial derivative of a function with more than one variable. And the partial derivative means that, okay, we're changing just one variable and holding all the other variables constant. Okay. So one example, one super simple example, here is a function of x and y. So this is a function of two variables. Let's now assume that it's could be x times y. That's one super simple example of an equation. Another one could be f of x, y could be equal to x squared times y plus 2x times y plus k. That's also a function of two variables, x and y. And this k here is a constant, by the way. So let's now look at one more specific example, so we can do some mathematics on that and some more numerical examples. So let's assume we have an endogenous variable. Could, for example, be the level of production that a firm produces. So we call that variable z. So z, level of production, for example, is then a function of two input variables, x and y. So this is the endogenous variable, and these x and y are the exogenous variables. They are given exogenously, and when you plug these in, voila, you get, from using this function, this endogenous variable z. So if you use this much labor and this much capital, you're going to get this much of production. Okay, so in this example, we're going to use a so-called Cobb-Douglas function. And you're going to be seeing that a lot in economics courses. So let's assume that we say x to the power of a times y to the power of 1 minus a. So this is an example of a Cobb-Douglas function. So in this particular case, we assume that a is set to 0.5. Set a equal to 0.5. Then we know that f of x and y is equal to x to the power of 0.5 times y to the power of 0.5. And you all know by now that this is the same thing as writing f of x, y is equal to the square root of x times the square root of y. Okay, so now we have this function. Fine, okay, so it seems to be increasing in both x and y. So if x is capital and y is labor, so if we increase capital and labor, we're going to get a higher level of production. Yeah, that seems reasonable. Okay, so can we draw this? Well, let's first look at, okay, what would be the sort of the numbers. If we input 0 capital and 0 labor, then if it's 0 here and 0 there, then we see that Z, the endogenous variable or the level of production, is going to be 0. What if we use 1 unit of capital and no labor? Then it's 1 to the power of 0.5, that's 1, times 0 to the power of 0.5, that's 0, so it's going to be still 0. What about 1 and 1? So x is 1, y is 1. Well, then we see that 1 times 1, that's going to be 1. Now, what if we have 1 unit of capital and 2 units of labor? Well, then we have 1 to the power of 0.5, that's 1, times 2 to the power of 0.5, that's approximately 1.4. Now let's say we have 2 units each of capital and labor, then we have square root of 2 times the square root of 2, that's 2. And here 1 and 4, so we have 1 here, that's 1, and then the square root of 4, that's 2, so it's going to be 2. So you can note here, by the way, that here we have a completely equal distribution of capital and labor, 2, 2, and we get the output level of 2. Here we have not so much capital, but a lot of labor, and the sum, you can see the sum of the units here is 5, the sum of the units here is 4, but even though we use 5 here, we only get 2. So you can think about that for the future. And finally, if we have 4 units of capital and 4 units of labor, then we have square root of 4 times the square root of 4. It's going to be 4. Okay, so that's how we would compute. So now you can draw your own diagram, you can dot sort of these levels here, and you can draw this. Now I have cheated. I have used a piece of software called GeoGebra. That is a free software that you can download, so you can draw these equations and play around with yourself. I can highly recommend that. Anyway, I have drawn this function that I've just shown you here, and here I have specified the function I want to plot, x to the power of a times y to the power of 1 minus a, and up here I can set a between 0 and 1, and I'll set it to 0.5. So the function I will be plotting is indeed x to the power of 0.5 times y to the power of 0.5. And here you can see in the diagram, you can see this is the x-axis, one of the exogenous variables, and here you have the y-axis, another exogenous variable, so this could be capital and this could be labor, for example. And on the z-axis, this is the level of the function, and this is could be in when we're discussing a production function, the level of output. Okay, so what would then this function look like drawn in 3 dimensions? Well, it's going to look something like this. You can see it's like a mountain going up, and if you increase capital and you increase labor, you're going to go up this mountain, right, and get a higher level of output. And we can also turn this around a bit. So looking at it from above, then you see the different coordinates here. So again, x-axis, y-axis, and then you have the z-axis here. That's like drawing something in 2 dimensions, but we are interested in this 3-dimensional version. And if we look at it from the point of view of x only, we can, there we go. So here, when we increase x, we see that we are going up the mountain, we're getting higher and higher values. And you see this line here, that is for, I think it is anyway, the y equals 1. So you can see that holding y constant and increasing x, we're going to go up the mountain in this direction. Okay, so that is how we illustrate a function of 2 variables. Now, you can imagine that we could have a function of 3, 4, 5 variables. Then, of course, it will be very hard to draw this diagram, but all the reasoning and the principles, they go through even though we use more than 2 variables. So, but it's much easier to show in a graph with 2 variable, so that's why we do it. Okay, so let's go on now and talk about level curves, which sort of describe different levels of production in terms of this function. Let's go back to that. So now you've seen this curve drawn, and another thing that we as economists, for example, are interested in learning about are level curves. And what are level curves? Well, for example, that's one level of production. So for example, let's say that Z, that was the level of output, is equal to 2. And we know that the production function is x to the power 0.5 times y to the power 0.5. And so a level curve shows you combinations of x and y such that z, that is a level of production, is equal to 2. So then the question is, what are those combinations of capital and labor, which represents different ways of producing a certain level of output? For example, you could have a very labor-intensive level of production with a big Y and a low X, or you could have a very capital-intensive level of production, a lot of machines, high level of X, low level of Y, and still you would produce exactly 2 loaves of bread, or whatever you're producing. So that's one question, sort of what combinations of X and Y do you need in order to get a specific level of production? So the more general case then. So then we have, let's say we fix the level of output at Z upper bar. So we're fixing it at some level. Could be 2, could be 4, could be 6, could be 2000, or whatever. And so on a level curve, let's say that, okay, we're keeping output constant. But then we can vary X and Y, but it must be so that the level of output is exactly Z upper bar. So then we have an equation like this. Okay, so now how could we then represent this in a diagram? So we will be interested in seeing, okay, for a certain level of X, what does Y have to be in order for Z to be some level? Well, let's then solve for Y. So let's redraw the equation. Z upper bar is equal to x 0.5 times y to the power of 0.5. Now, if we want to have y on its own, let's start by dividing both the left-hand side and right-hand side by x to the power of 0.5. Then we can see that, well, okay, these two cancel because this is equal to 1, right? So we don't have to bother about this. And so we can rewrite the equation again. Let's put y on the left-hand side. Y to the power of 0.5 is equal to z upper bar divided by x to the power of 0.5. We're not quite satisfied yet because this thing here is to the power of 0.5 and we just want to have y here. So what do we need to do? Well, you know from previous classes in exponents and stuff, that in powers, that we need to raise this, the left-hand side and right-hand side, to the power of 2. Because then looking at the powers, raising this to the power of 2 is going to be, the new power here is going to be 0.5 times 2 is 1. And that's what we need. So we'll do that. So we're raising the left-hand side to the power of 2. But as always, we need to do the same on the right-hand side. To the power of 2. Okay. So on the left-hand side, we have y to the power of 0.5 times 2. That's y to the power of 1, which is just y. Very good. Y equals. And what do we have on the right-hand side? Well, we have z to the power of 2. That's, well, z upper bar to the power of 2 divided by, and we see that 2 times 0.5 is also 1. So we have z upper bar squared divided by x. So now we know for a given value of z, namely z upper bar, for any given value of x, then y has to be this. Okay. So let's look at one example. Say x is equal to 2. What does then y have to be? Well, then that means that y is equal to z upper bar squared divided by 2. And there you have it. And for example, if we say that z upper bar is equal to 2, that means that for the level curve where level of production is 2, and we set x equal to, what is then the value of y? What is going to be y is equal to, then z upper bar was 2, so it's 2 to the power of 2 divided by 2 is equal to 4 divided by 2 is equal to 2. Wow! Okay, so remember this. If we are at the production level of 2 and x is 2, then y has to be 2. So let's see if that is true in our graph. Now we're back with our old graph here. And one thing that's interesting to know is for what combinations of x and y do we have a certain level of production, the level curves that we just discussed. Okay, so I have prepared one level curve for you, namely the one where we have a level of production of 2. And if we draw that level curve, we see it's this one here. And if we tilt the diagram on the side, we'll look at it from the perspective of good x, then we can see that here the level curve is indeed at the level 2 of output. Okay, so the interesting thing here is to see, okay, for what combinations of x and y do we get this level of production? So one easy way of doing that is, in fact, to just take the drone view, look at this mountain from the top. Let's do that. There we go. And so again, this is the x-axis, this is the y-axis, and the z-axis is just pointing straight up against us here. So this is like if you have seen a map, a topographical map in reality, then you know hills are denoted by sort of level curves as well. So having many level curves like this is going to denote a hill. And that is exactly what this is. This is a level curve. So here we see that along this line we are at the same height over the ocean. We are at the same level of production. So here we see that the point 2 of x and 2 of y, that's 2 units of capital, 2 units of labor. And then we see that, oh, it's this point here. And oh, yes, it's on the level curve at the output level of 2, which is indeed what we wanted to check from before. Okay, so it seems to be correct. And we see that, okay, there are different ways of producing. You know, this is kind of using 50% labor and 50% capital. Going down here, this will correspond to a very capital-intensive level of production with lots of capital, not so much labor. And going up this way, we would have to use a lot of labor to compensate for the little amount of capital that we're using. Okay, so that's how you can economically interpret one of these level curves. Okay, so this is for the level of 2 units of output. So how would the same type of curve look for 2 units of output? Well, let's look at that. Well, that curve is going to be out here. Okay, so it takes more labor and more capital to produce 4 units of output. So this is 2 units, 4 units, and what about 6 units? Well, that's going to be out here. So indeed, now this is starting to look like a topographical map. So this is 2 units above sea level, this is 4 units above sea level, and this is 6 units above sea level. And you can see that you see that here we have we have 2 units, 2 units. This is 4 units, 4 units. This is 6 units, 6 units, and it corresponds to the level of output. So this should be correct. And again, turning this on looking at a three-dimensional view, you can see that yes, this is indeed a mountain with these different level curves. So, what is a partial derivative? Well, let's see. Now, before in this course, we looked at the following thing. Before, we had a function, we looked at functions of one variable. For example, f of x, that's a function of one variable. And when we took the derivative of that, we drew it like this. Or we would write it like this. D f of x dx. And another way of writing that would be f prime x. So how much does the value of the function f of x increase when we increase the use of x by one super small unit? Okay, that is a slope, and that is the derivative. Okay, now we have the following. Now we have f of x and y. And if we want to take a partial derivative, namely how much will the value of this function increase if I increase the use of only x by one super small unit? Okay, it is then written like this. D f x y dx. Now, this is called a curly d. I know, it sounds silly, but it's called a curly d. And the only point of writing the curly d instead of the d is that since we have a function of two variables, and we want to be super clear in saying, okay, this is a partial derivative. That is, we are looking at how much does this the value of the function change when we change only x, holding y constant. That is what that means. And the notation for that, an alternative notation for that is also f prime of x. Okay, and of course, if we are looking at the partial derivative with respect to y, because this was with respect to x, it will be the following: f of x, y. Then the partial derivative of this function with respect to y is then written as df x y dy. And another notation would be f prime y. And the main thing to remember is that when you're taking a partial derivative with respect to either x or y, then you are holding all other variables constant. They do not change. You change one variable at a time. Let's look at how we can illustrate that in a graph. So how can we illustrate the partial derivative in this graph? Remember that the definition of a partial derivative is how much extra production do we get if we increase the level of x by one tiny unit. Okay, so let's assume that we are at one point in this diagram. Let's say we are at point A, which is exactly here. It corresponds to the point where x is 4 and y is 4. Okay, so, and let's assume now that we increase the level of x from 4 to 5. So we move from point A to point B. Now we know in terms of when we're supposed to define derivatives, the change must be very small, but in order so I can show you, I'm going to make the change 1 unit here, which is quite long. So we are then moving from point A to point B, and you can see here in the three-dimensional graph that yes, we are moving a bit, along the x-axis, that is going east, right? Because the y-axis is north and south, and the x-axis is east and west. So yes, we are going east. And how much higher up do we get on the production mountain? Well, that is the question. So let's look at this from another perspective. So if we take the drone perspective, so let's say we have a drone and look down on this mountain, and we can see that, okay, this is the x-axis, or I guess you call it capital, and this is the y-axis, the labor. So we can see here, moving from A to B, we have increased the level of x by exactly 1 unit. And remember that when you take the partial derivative, you hold the other variables constant. And the other variable in this case is y, which is measured here. And you can see that we are moving along 4 here, right? This line. So we are not changing y at all. We are only changing x. Okay, so, but this doesn't show us how much higher we get. This just shows that we are indeed increasing the level of production because we are moving above this isoquant, this level curve here. We are to the right of that. So let's look at this from the side, from the point of view of x. It's a bit tricky, but I will hopefully succeed. Okay, so now you see it from the side here. So this is the x-axis here, and the y-axis goes straight in, and the z-axis, the level of production, goes straight up. And we moved from point A to point B. And then the question was, how much more output do we get for that change in x? Well, it is the vertical distance between the orange line, the level curve here, and the point B. So this is the change in the level of production we get from increasing x by 1 unit. Okay, what is then a partial derivative? Well, that's the rate, that is how much higher up do we go when we move 1 step to the right, as I said before, and that's a slope. And we can illustrate that by drawing a line like this. So ideally, when we're talking about the derivative, we must evaluate the slope of the tangent here at point A, because now it is the line is drawn between point A and point B, but if we would slide point B much closer to point A, then we will get h approaches 0 as in the definition of a derivative, and then we will look at the slope and we see how much higher up do we get from moving 1 unit to the right. And that is what the partial derivative means here. So how much extra production when we increase x while holding y constant. Now let's get back to how we can calculate a partial derivative. So let's take one example. Let's say we have this function f of xy is equal to the one we were just looking at, namely x to the power 0.5 times y to the power 0.5. Okay, what is then the partial derivative of this function with respect to x? Okay, let's calculate that. So the curl d, the partial derivative of this function with respect to x. So how would I then calculate that? Well, now, as I told you, we think of y as a constant, like any other constant. So we don't have to think about this so much. This is just a constant. So what we need to focus on is this one. What is the derivative of x to the power 0.5? We know that is 0.5 times x, and then the power is going to be 0.5 minus 1, that is to the power of minus 0.5. And then we just multiply by the constant y to the power 0.5. So this is the partial derivative of this function with respect to x. We can of course rewrite this a bit. This is equal to square root of y, this thing here, divided by the square root of x, because x to the power of minus 0.5, that's 1 divided by the square root of x, and 0.5 is the same thing as divided by 2. So this is the partial derivative with respect to x. So this is one example. Another example, so let's assume we have a function f of x and y, fxy, is equal to x to the power 2 times y to the power 2 minus 2xy. So what is then the partial derivative of this with respect to y. Okay, the partial derivative of the function with respect to y, that's why you do curly dy here, holding x constant, is then equal to, well then x becomes a constant, so that just remains there. So this is x squared, and then we have the derivative of y to the power 2, that's 2y, so we have to put a 2 here and a y there. And what about this term here? Well, x is a constant, so it remains, 2 is a constant, it remains, so we're just going to have minus 2x. That was the second example of a partial derivative, but this time with respect to y. That's all for this time. See you again.